Good afternoon, everyone, and welcome. I'm Dr. Luciana Borio, Acting Chief Scientist at the FDA. I'm very pleased to be here this afternoon to launch the FDA Grand Rounds. And for those of you who are less familiar with FDA's research programs, I really want to emphasize that it is a critical component of FDA's mission to protect and promote the public health. Science is at the core of everything that we do here at FDA. It underpins all of our regulatory decision-making. We decided to launch these grand rounds to give you a richer understanding of the depth and breadth of our research programs. Many of our 11,000 scientists are hard at work in our labs here at White Oak and across the country, answering some critical questions about the range of products that we regulate. The research gives our reviewers the information they need to make science-based decisions about a product's benefits and risks. Our speaker today, Dr. Tod Merkel, is a principal investigator in FDA's Center for Biologics Evaluation and Research. He brings more than 25 years of experience to the study of bacterial pathogenesis and the evaluation of new vaccines. Dr. Merkel will be speaking on the host response to pertussis infection and vaccination for about 45 minutes, and then you'll have a chance to ask questions in a 15-minute Q&A session. So, without further ado, please welcome Dr. Tod Merkel.
All right, thank you. It's a real pleasure to be invited here for this kickoff FDA Grand Rounds. I am going to be talking about the work we're doing here in our lab at the FDA on the host response to pertussis infection and vaccination. Oops. So pertussis, it's also commonly referred to as whooping cough, is a highly contagious respiratory infection caused by Bordetella pertussis. It's actually not a very ancient disease. The earliest known description of pertussis in the literature was in the 15th century, which is actually very late. Most human infectious diseases have been described in even the most ancient literatures. As we may talk about later, I personally think that probably reflects the nature of pertussis, and that is it's a human-only pathogen, and in order for it to be maintained, it has to be transmitted constantly from one person to the next. So it requires this airborne, unbroken chain of transmission. And probably the conditions that allowed for that to occur required large, dense populations of people, and dense populations of that size probably didn't exist until relatively late in human history. In order to really appreciate the severity of pertussis, I think you have to think about the pre-vaccine era. In the pre-vaccine era, pertussis was nearly universal by school entry. So what this means is virtually almost every child got pertussis by the time they were 5 years old. Approximately 1 in 10 cases resulted in mortality, which resulted in pertussis being responsible for more deaths than measles and polio combined in the pre-vaccine era. I think the fact that we don't often associate pertussis as being really a severe problem is a testament to the effectiveness of our vaccine program. But despite our vaccine program, it's still one of the 10 most common causes of death from infectious diseases worldwide. If we look at, see if I can use this arrow here. If we look at the history of pertussis reporting in the United States, you can see that in the pre-vaccine era, we did have a really large number of cases, 150 to 250,000 cases per year in the United States. And this is, of course, at a time when the population of the United States was much smaller than it is today. With the introduction of a whole cell vaccine in the 1940s, we drove the incidence of pertussis down almost to zero. but not to zero. Unlike other infectious diseases like diphtheria and tetanus, where we essentially eliminated the disease in the United States, we never achieved that with pertussis. With pertussis, the lowest number of cases we saw was in the 1970s and 80s, where we averaged about 1,000 cases a year. What's alarming to us in the public health sector is what we've seen in the last 10 to 20 years. It's not really strongly noticeable, but you can see here that in this period, from the 1990s to the early 2000s, we just had a very slow but steady increase in the number of pertussis cases. But really markedly in the last 10 years, we've seen a really significant increase in cases. In 2012, we had almost 50,000 cases of pertussis in the United States, and we've never seen levels like that since the introduction of vaccines back in the 1940s and 50s. I like to emphasize that 50,000 cases a year itself is not what is alarming. What is alarming is this obvious upward trend. And it really needs to be emphasized that we do a very effective job of vaccinating our population. Unlike other infectious diseases where it's really clear that epidemics and outbreaks are due to vaccine refusers is not the population that's driving the increase in pertussis in the developed world. In the United States, for example, almost 96% of children entering elementary school are fully up to date with their pertussis vaccinations. In 2006, we introduced an adolescent booster vaccine that's given to most kids before they enter middle school. And by 2012, and now in 2014 and 15, over 80% of children entering middle school have received that booster. So I don't think we can reasonably expect to vaccinate at a higher rate than we're already vaccinating. And despite this really high rate of vaccination, we have this steady increase in the number of reported cases here in the United States. So this is a problem that we need to understand and try and come up with solutions. And one of the problems with studying pertussis, as I mentioned, is it is a human-specific pathogen. It doesn't cause disease in most other animals or in any other animals that have been tested. So we really needed a model, an animal model, that provided a way to study pertussis disease and infection and transmission and vaccinology. And in order to do that, we eventually developed a baboon model of pertussis that I'm going to tell you about now. So when we challenge young baboons with pertussis, we see that, as is the case in people, you see a large number of pertussis. You can isolate a large number of pertussis from their airway. And the way we do this is by just flushing saline through their nose into the nasopharynx and recovering it and plating it. And you can see a challenged baboon is highly infected, and that infection persists for about 4 weeks. And although we routinely test by testing the number of bacteria in the nasopharynx, we have done studies where we've used a bronchoscope to sample bacteria throughout the airway. Because what we wanted to assure ourselves is that what we're measuring up in the nose is representative of what's going on throughout the airway. And we also wanted to determine whether there were differences in our studies where we just directly introduce the bacteria versus studies where we allow animals to be infected by natural transmission of the bacterium. And what we found is that no matter where we sample throughout the airway, whether it's up in the nose or all the way down into the lower bronchi, we see very high numbers of bacteria, and it doesn't seem to matter whether it's a directly challenged animal or an animal that was infected by transmission. And this gives us a lot of confidence that what we're studying in our model is very real and the results are meaningful. The infected baboons exhibit leukocytosis. This is a hallmark of pertussis. Kids who have pertussis have really extraordinarily high white blood cell counts. So what we're showing here is the number of white blood cells we isolate per microliter of blood. And so here we typically see 50, on average about 50,000 white blood cells per microliter of blood. Young infants with pertussis can have white blood cell counts in excess of 100,000 white blood cells per microliter. Pertussis is sometimes initially misdiagnosed based on the blood testing as leukemia. But when you see a kid coughing or with respiratory distress and high white blood cell counts, you can be pretty sure you're looking at a case of pertussis. And this is also the case in the baboon. Also, another hallmark of pertussis is that it does not induce a fever. And this is really important because this is also an important diagnostic in kids, and that you have a very sick kid, but a kid who has no fever. This is very typical of pertussis, and it's also what we see in the baboon. Interestingly, in the laboratory, we've shown that pertussis that's grown at 39 degrees, which is just 2 degrees above normal body temperature for people, the bacterium doesn't grow, and it doesn't induce and it doesn't produce virulence factors. So what this is telling us, I think, is that pertussis actually can't tolerate a fever, and therefore it probably deliberately avoids causing a fever, or maybe actively prevents fever from being induced. All right, we're not advancing anymore. There we go. Okay. So we think that when you look at the infection that we get in the baboon when we infect them, that it looks very much, almost indistinguishable from the pertussis that's observed in young kids. So we were confident that we had a good model for studying pertussis. And the first thing we wanted to look at was the host response to infection. And so one of the easiest things to do, and one of the first things to look at, is humoral responses, antibody responses. And you can see that in infected animals, you see significant antibody responses against at least the antigens we looked at, which are the antigens that are found in the vaccines that are used in the United States. As well as here, this is just whole cell heat-killed pertussis on a plate. So you get a good antibody response against the whole bacterium. And the other thing we noted is that infection induces a very protective immunity. So I'm going to talk a lot today about convalescent baboons. A convalescent animal is an animal that was infected with pertussis, had disease, and then recovered from disease, and then we subsequently reinfected. So what we're looking at is the immune response that's induced by the infection. And when we take animals, convalescent animals, and reinfect them, they don't get sick at all. They have no outward sign of disease. They're very happy and active, and we see no change in white blood cell count, which is a really good marker of disease. And we also find that we're unable to isolate any bacteria from the airway of these animals. So the immune response that's induced by an infection is a really good protective immune response, and it prevents reinfection and of course prevents disease. So one of the things we wanted to look at was cytokines. What was the nature of the immune response that's induced by infection? And we looked at a whole panel of cytokines, and what I'm going to show you now are the only cytokines that we were able to detect in these animals as being elevated by infection. So when we look at the mucosal fluid from the nasopharynx, from the airway, we saw strong inductions of IL-6 and IL-23 and IL-1 beta. And we also looked specifically at IL-17 and saw a strong increase in IL-17. So this is at the mucosal surface of the airway. And then we saw also GCSF, MCP1, and IL-8, which are IL-17 induced chemokines and cytokines. And the reason that I think it's significant that these are the only cytokines we saw is that these cytokines are what you expect when you have a Th17 response. And Th17 responses have been shown for other extracellular mucosal pathogens to be really important or to be required for clearing those bacteria out of the host. And so the way that response works is you have antigen-presenting cells. They produce the IL-1 beta, IL-6, and IL-23, which we saw. And this induces Th17 cells to produce IL-17, which is also a cytokine we saw. And the IL-17 induces the mucosal epithelial cells to produce the chemokines that recruit neutrophils. And neutrophils are really excellent bacterial killers. They take up bacteria and they kill them very effectively. And we think this is the response that's responsible for that sterilizing immunity that we see in convalescent animals. Because they have a good Th17 response and because they recruit neutrophils to the airway mucosal surface, the body is able to rid the airway of the bacterial cells. So we now went on to start evaluating the vaccines that are used in the U.S. And what we saw, so now we're comparing naive animals that are uninfected or were uninfected versus convalescent animals that are animals that have recovered from infection, and animals that were vaccinated with the same vaccines that we use here in the United States, acellular pertussis vaccines. And again, vaccinated animals were very well protected from disease. I mean, they were perfectly happy, very active, no outward signs of illness, and they had no increase in white blood cell counts. But what really startled us, and I think it's fair to say we were startled, was that we found that these acellular vaccinated animals, even though they're not sick, they are infected. So they have very high numbers of bacteria in their airway, and those bacteria actually persisted longer in the vaccinated animals than in the unvaccinated animals. But again, it's important to point out that the unvaccinated animals, although they cleared faster, they were very sick. I don't know if we can get tech help. I'm having a very hard time getting the slides to advance. Now, we were a little bit concerned that, when we do directly challenge animals, we give them a really high dose of bacteria. And so we were sensitive to the criticism that perhaps the acellular vaccine immunity was being overwhelmed by that very high initial dose of bacteria. So we did an experiment where we took vaccinated animals and an unvaccinated animal and housed them together with an animal that was infected. So now we weren't looking at a challenge scenario, we were looking at a natural transmission. And even in this case, you can see that the acellular vaccinated animals, although they were not sick, they were infected and colonized for the same period of time and at the same magnitude as the unvaccinated animals. So the vaccine was not protecting these animals against infection, although it was preventing them from getting sick. So this raised, I think, the really important question is, can these animals that are vaccinated, who are not showing any symptoms but who are infected, actually transmit the disease? So what we did was we took animals, two animals that were vaccinated, we infected them, and then in separate cages we co-housed those two animals with naive animals. And in both cases, and this is the open circles of the naive animals, in both cases you can see that the infection was transmitted from the asymptomatic vaccinated animals to their cage mates. So what we've learned by this time is that although the acellular vaccine protected very well against disease symptoms, it didn't prevent infection, it didn't prevent carriage, and it didn't prevent transmission to naive animals that were housed in the same space. So we next turned our attention to whole cell vaccines. So whole cell vaccines were replaced in the United States in the early 90s. with acellular vaccines. And the reason that that was done was because the whole cell vaccine is pretty reactogenic. So kids who are vaccinated with the whole cell vaccine, they'll have significant pain at the site of infection. They'll usually have a mild fever. Some kids will have a pretty severe fever. And because of this reactogenicity, the acceptance of the vaccine was going down. And so the vaccine was replaced with the acellular vaccine that doesn't have that reactogenicity problem. But whole cell vaccines are still used throughout the world. And we were able to get some whole cell vaccines that are used in other parts of the world and do these experiments. And what we found was, again, whole cell vaccinated animals were protected very well from disease. They were very active and had no white blood cell count increase. And although they were initially infected at the same high level as acellular vaccinated animals, you can see that they cleared much more rapidly than the acellular vaccinated animals or the naive animals. Now, this difference in days to clearance is a very reproducible result. We see that the whole cell vaccinated animals do clear faster than acellular vaccinated animals. And we also see that acellular vaccinated animals take longer to clear than the naive animals. When we try and look at the differences between acellular vaccinated animals and whole cell vaccinated animals, we don't see a difference in antibody responses or humoral responses. For at least the vaccine antigens and whole pertussis, we see very high antibody responses in both populations. Now, it's important to point out that a whole cell vaccine has all the antigens that are present in the bacterium. So if we tested an antigen that wasn't present in the acellular, we would likely see a response in the whole cell group, but we would not see that in the acellular group. So one of the advantages of a whole cell is you get a broader responses to a broader range of antigens, and that might very well be important here. But one of the things we think is really significant is the exposure that you have determines the skewing of your adaptive immune response. So if you look here, you can see that in a convalescent animal, an animal that has recovered from infection, that animal has a really strong Th1 response and a very strong Th17 response and virtually no Th2 response. And it's really striking, I think, that the acellular vaccine gives you almost the opposite profile. It gives you a low Th1 response, an almost non-existent Th17 response, and a very, very strong Th2 response. The whole cell vaccine sort of has the same profile as natural infection in that it has a Th1 response and a Th17 response and no Th2. It's just the magnitude is much lower. And this correlates with the ability to clear infection in that convalescent animals clear the infection very well, whole cell vaccinated animals clear the infection, but not as rapidly. So what we think this is telling us is that in order to prevent disease symptoms, you need a good antibody response. You need a good Th2-mediated antibody response, probably against the toxin. But if you want to clear the infection out of the airway, you need a cellular response. You need to recruit neutrophils to the site of infection, and for that, you need a Th17 response. Now, I'm going to finish up today by talking a little bit about the work we're doing looking at maternal vaccination, because we think that protecting newborns is probably the most important public health issue related to pertussis. And the reason for this is because the disease is most severe in infants. The most hospitalizations that occur due to pertussis are in infants under 2 months of age, and the vast majority of deaths occur in children under 2 months of age. And the reason for that is twofold. One is these infants are just very small, and their airways are smaller, and therefore they have more difficulty dealing with pertussis. But the other issue, of course, is that they're not vaccinated. In the United States, we vaccinate at 2, 4, and 6 months of age. So infants under 2 months of age have no immunity to pertussis. and therefore they have the most severe disease. And this is the population in which we see deaths. So one of our goals is to figure out a strategy for protecting infants in that window of vulnerability between birth and 2 to 3 months of age when they can start to benefit from vaccination. And there have been several strategies put forth in order to achieve this. One of the thoughts was that when we introduced the adolescent booster, that would protect newborns as well, because adolescents with disease was probably a source of exposure of infants. And what we found was that the introduction of the adolescent booster reduced pertussis dramatically in the adolescent population, but really had no impact on the newborn population. And in hindsight, it's been explained to me that that's because there's actually very few households in which parents have adolescents and newborns. And actually, adolescents don't hang out with newborns very much. So there's actually very little contact between those two populations, and there was probably never very much transmission between them. Another attempt was cocooning. And the idea here was, or is, to vaccinate the adults that have the most contact with a newborn. So the parents, the kids in the house, if there are grandparents that are visiting, grandparents in the house. It's certainly true that infants that belong to large families are more likely to get pertussis than infants that belong to small families. You know, if you have a lot of relatives coming over to visit the baby, then the likelihood of exposure is higher. So the notion was if you could vaccinate the people that kids are exposed to, you could prevent them from getting infected. And there are two problems with that approach. One is it's very, very difficult to vaccinate adults. You know, you've got to get them to go to their doctor and get the shot, and it just doesn't happen very readily. So this is a very difficult strategy to implement. It's also very expensive. To protect one newborn, you have to vaccinate a bunch of adults. And finally, our results show that even if you are vaccinated, you can be infected. And if you have enough contact with a newborn, it's likely you can transmit to that newborn. So our data would say that this approach is less likely to be effective. Another approach is neonatal vaccination. This has been shown to work. We've actually shown it in the Baboon model, although I'm not going to show that data today. And the idea here is you vaccinate a child on day 1 or 2 before it leaves the hospital, so that it can be protected sooner. And that is an effective strategy, but it still leaves a window of vulnerability in the early weeks. And finally, the strategy that is being discussed and implemented actually is maternal vaccination. So the idea here is to vaccinate a woman in the beginning of her first trimester of pregnancy, or early in her first trimester of pregnancy. The idea being that antibodies will be transferred transplacentally to the infant, and those antibodies can protect the infant in their first year of life. So we wanted to test whether or not this strategy was likely to work, so we tried this in the baboon model, and we vaccinated pregnant baboons at the start of their 3rd trimester, and then we waited until the infants were born, and then we challenged the infants at 5 weeks of age. So the first thing we looked at was the antibody titers in the mothers and in the infants at the time of the challenge. And one of the things that I found striking, at least, was that this demonstration that this transfer of antibodies across the placenta is an active process. And that's shown here by the fact that the antibody titers in the infants was actually higher than their mothers. And I mean, lots of people already knew that. I didn't, so I thought it was kind of cool when I saw it. But when we challenged these infants, again, we saw that they were infected and that they had high numbers of bacteria in their airway, out for 4 weeks. But we didn't really, we weren't really concerned about that because we weren't trying to protect infants from infection. We were trying to prevent them from severe disease. And we found that this approach actually did protect them. The infants that were born to vaccinated mothers were just totally fine. They had no increase in white blood cell counts. They had no loss of activity. They looked just perfectly normal and happy and had normal activity. So what these results told us is that maternal vaccination, even from a really, was able to protect infants even from a really robust challenge, and that this approach is likely to work. So the work in the lab now is focused on first of all, understanding the disease better, understanding the pathogenesis of the disease better, but also looking ahead, because what we think that what's needed is a next generation pertussis vaccine that protects not only against disease symptoms, but also prevents infection, or at least results in rapid clearing of the bacterium after exposure. And we think what's needed is a good antibody response, so a Th2 response, but also a Th17 response directed against the right antigen so that the bacteria in the airway will be targeted. So we think probably the next generation vaccine is going to need different adjuvants than the current one, perhaps additional antigens, and perhaps the route of exposure or the route of delivery of the vaccine will be important. So trying to understand these things is what we're focused on in the lab these days. So I just want to thank the folks in my lab. Jason Warfel is a former postdoc in the lab who did most of the provided most of the immune response data you saw today. Elizabeth Schoenfeld is picking up where Jason left off, and Lindsay and Laura are technicians in the lab who help with all aspects of the work. We have a really fantastic NHP program here at CBER that makes this work possible. Jill Asher is the DVM who I work most directly with the primates. The program is headed by John Dennis, and Lewis and Perry and Faith are vet techs who, again, are involved in all aspects of the work. And at the Oklahoma Baboon Research Resource, Roman Wolf and James and Stan Kosaki basically taught me everything I know about baboons. So I really appreciate their help. And Nicole is a vet tech out there who's helped us a lot as well. And all of this work is funded both by the FDA and by the NIH, the NIAID, the MIT. Thank you.
Great presentation. I was just curious if you think it matters which trimester the baboons are vaccinated, and if lactation, if you've ever looked at whether lactation made a difference.
Right. So we haven't done these studies in the baboons. What we focused on in the baboons are infection studies, because that's the one thing we can do that you can't do in people. But there have been quite a few studies where they're looking at the timing of when you vaccinate a mother and the amount of antibody that gets transferred to the infant. And if you vaccinate early, then the mother's immune response will actually peak and wane before she's at the point in her pregnancy where she's really transferring a lot of antibody. And if you vaccinate too late or just before delivery, then there's not enough time. So sort of the optimal time to vaccinate is early in that third trimester. That's when you see the highest titers in infants. And we don't know. We haven't been. It would be really extraordinarily difficult to do studies to distinguish between lactation, antibodies in the breast milk, and transplacental antibodies. And that's because we keep the infants on the mother as long as we can. You'd have to take the infants off the mother at birth in order to start looking at that.
Thank you. We have a question here.
Okay.
There has been a great deal of discussion regarding whether or not vaccinating the mother while pregnant lowers the response of the infants to the vaccines they receive at 2 months. Have you studied this?
Well, we haven't studied that personally, because as I said, that's a study that's better conducted in kids, because it can be conducted in kids. There is some evidence, but I mean, different studies have had different results. Some studies have seen no impact on the vaccinations given at 2 months. Some studies have seen some impact on the vaccines given at 2 months. Those studies where they saw an impact at 2 months those kids caught up by the 4-month, after the 4-month vaccination and the 6-month vaccination. So the sense is the trade-off is probably worth it, because the disease in kids under 2 months of age is so severe, and that's where the deaths are. It's probably worth the trade-off to have a slightly lower response at 2 months than have no response, have no protection between 0 and 2 months. And that's the reason why it's recommended.
I was wondering whether in the countries where the whole pertussis vaccine is still given, there is an effect on the infants that are born from women that receive that vaccination. And whether, since we don't have a better vaccine for now, there was consideration to maybe give whole virus vaccine to adults and leave the cellular pertussis vaccine for infants, and whether you considered maybe testing female baboons before they get pregnant, let's say 6 months before they get pregnant.
Well,
because there is this effect of concentrating antibodies.
So I've got to try and pick apart your question,
Yeah.
right? So the first question
the
is
differences between cellular and whole, and also effects of vaccinating before.
vaccinating the mother before pregnancy in order to protect the infant.
Yeah, I mean.
Well, the reason that's less effective is because by the time the mother delivers, her titers are down, and therefore the amount of antibodies she passes to the infant is also down.
That's right.
But
for many infections, I mean, mothers get infected before they get pregnant, but still they manage to transmit something to infants because for 6 months, for many diseases, infants are protected. So that's why I was asking.
Well, in the pre-vaccine era, not the wholesale era, but in the pre-vaccine era, we virtually saw, or believe we saw, virtually no pertussis in newborns. And the reason for that, we believe, and this is just hand waving because nobody looked at it back then, is that probably because every single kid got pertussis by the time they were 5 years old, it was circulating in the population constantly. So once you got your pertussis when you were a kid, you were constantly re-exposed and boosted, so you always had good immunity, high titers. And so that mothers who had children, they had high titers, and transferred those titers to their infants. So that's what we're actually trying to mimic with maternal vaccination.
We have another question here. Could you comment on routes of administration you mentioned as an important feature requiring further investigation?
Right. So our thinking here is that when you compare even wholesale vaccinated to animals that have recovered from an infection, animals that have recovered from an infection are completely protected. We can't isolate bacterium back out of them. The wholesale vaccine animals are protected better, but not even as well as convalescent animals. And there are two differences there. One is the convalescent animals were actually infected in their airway at the mucosal surface, whereas the wholesale vaccine is given intramuscularly or parenterally. The other difference, of course, is that in the infection, you have replicating bacteria at the airway. And those replicating bacteria probably are really sending off alarm signals to the host response. So we think that you may, with essentially the same antigens, get a better response if they're delivered mucosally than you would if they were delivered parenterally. And that's something we're actively studying right now.
So, sorry if I missed this, but the product that you were using to vaccinate the mothers, commercially available, like one of the Tdaps,
Yes.
Boostrix, or Adisol?
Both. And so, I mean, for those of you who may or may not be aware, there are two companies that distribute pertussis vaccine in the United States, GSK and Sanofi. And so we use a representative vaccine from each one of those two companies in all of our acellular vaccine studies, because the antigens are probably slightly different, and we want to make sure that our studies are representative. Fortunately, we've never seen a difference between the two products, so that simplifies our life. But in these studies that I've shown you for the maternal vaccination studies, we use the Sanofi acellular and the GSK acellular.
Yeah, so I'm wondering, have you thought about trying to use a pertussis toxin only product in that model of maternal vaccination, and or the mucosally delivered live attenuated? Some of the investigational products that I think have been published on, but have you considered trying them in the maternal vaccination?
We are, as we speak, testing a pertussis toxin only vaccine, and the preliminary data is that shows that that is sufficient for protection.
To protect the newborn in that same...
Yeah. I mean, we wouldn't test the live attenuated in a maternal vaccination study, because I can't imagine it would ever be used in that setting. But we are testing live attenuated vaccine, in our infant vaccination studies.
Thanks, Todd. That was really interesting. I have a question about the high rate of fever with whole cell. And I think it's interesting that with natural disease, you don't really see fever.
Right.
And is this related to route of administration, and it's just that this is that pertussis is something that happens locally, in the airways? Or is there some other explanation for why we would see high rate of fever with whole cell vaccine but not see it in natural disease?
Well, I can only speculate, but I'm happy to speculate. So I mean, it can be one or the other. I mean, definitely infection is obviously by a mucosal route versus a parental route, and that may explain the fever. Alternatively, and this is the explanation I prefer, I think pertussis actually probably actively prevents the induction of fever because it can't tolerate it. Thank you. Oh. So I've been asked to tell everyone to please join us for our next grand rounds in May. Patrick McDermott from the Center of Vaccine Medicine will be presenting on antibiotic resistance surveillance in the age of genomics, new answers to old questions. Thanks. Thanks. Yeah, I mean, I can show you the preliminary data. There's two things that there's two things that are really nice about it. One is toxin only is enough. Right, so for like the developing world, that might be a good way to go. I don't know though. I just that Gates meeting down in Atlanta. So I mean, I don't know what Gates is going to do, but basically they brought in all these people that are doing all these surveillance studies and development. And Gates is really high on the idea of implementing maternal vaccination for pertussis. And all of these people who are like boots on the ground in all the countries, the basic message was pertussis might be a problem, but we can't see it because these kids are all dying from so many viruses. Right? So I mean, it's like if we eliminated pertussis in Africa, you wouldn't even notice it because there's so many other terrible things going on. So I don't know what they're going to decide to do, whether they're going to back off or keep talking. But I think the genetically inactivated? Yeah. It's not even under patent. Anybody. Yeah. But, the NIH had the original patent on that. Well, no, that's our goal. That's our goal. Well, there's something even better for the U.S. But the other thing that's really interesting is I think we're going to be able to show that protection, there's a threshold of protection. Because we already have, just so happens that, so one of the issues we have is that we didn't want to use primed baboons. It just takes too long to prime them and then wait and then boost them. So we're just using naive baboons. So we're not getting really great responses to the vaccine, but we're getting responses. And it just so happens we're like right at the threshold because we're having animals that have high responses to protective. We have animals that have lower responses and lower responses. So we want to add animals so that we can do like a half dose. And I think we're going to span the whole range of protective doses. Yeah. I know of at least one company. I know that there's one company that's pushing their toxin on this because they figure that's their way to they're marketing. They're going to market.
I mean, I'm just blind. What's going on here?